We're now going to apply the aromaticity rules to determine whether compounds based on their structures will be aromatic, anti-aromatic, or non-aromatic. We'll start with the monocyclic hydrocarbons, which are often called annulenes. The simplest example, or one of the simplest examples, is cyclobutadiene, which has the following structure. Notice it has 2 double bonds, and as a result, it has 4 pi electrons. Each carbon in this cyclobutadiene is sp2 hybridized, so that means that it has a p orbital at every carbon atom. So based on the small size of the ring, this molecule would be flat. Obviously, it's cyclic. As we mentioned, it has a p orbital at every atom, so it has an uninterrupted pi cloud, which means that this compound follows rule 1 from the aromaticity rules. Now, because it has 4 pi electrons, it doesn't follow Huckel's rule. Instead, it follows the rules based on anti-aromaticity. So this compound would be predicted to be anti-aromatic. That means that this compound is very unstable, and it should come to no surprise that the compound is so unstable that it actually reacts with itself through a reaction called a Diels-Alder reaction, where the molecule dimerizes and it makes this dimer shown here. As we discussed previously, benzene is an aromatic compound, but let's see, based on the aromaticity rules, why that is. First of all, benzene is a cyclic molecule. It has an sp2 carbon, as you can see by the double bonds at every carbon in the ring. That means there's a p orbital at every one of these carbons. The molecule is flat as well because of the sp2 hybridization of each carbon, which would force each carbon to be trigonoplanar. And so overall, the ring itself would be a flat ring. That means that this compound follows rule 1 of the aromaticity rules, in that it has an uninterrupted pi cloud. It also follows rule 2, or the Huckel rule, because it has 6 pi electrons. So you might recall that the Huckel rule says that if a compound has 4n plus 2 pi number of electrons, then it would be aromatic as long as it follows rule 1 as well. So in the case of benzene, we have 6 pi electrons, which is an example of a compound that follows Huckel's rule. So if we plug in 1 for n in this formula, we can come up with 6 pi electrons. So that's an acceptable number for an aromatic compound. Cyclooctatetraene, which is shown here, is a compound that has an sp2 carbon at every atom in the ring because of the double bonds. That means there's a p orbital at every atom. The molecule has 4 double bonds, so as a result, it has 8 pi electrons. So based on the rules of aromaticity, this compound would be predicted to be anti-aromatic based on these rules. Now, that's only true if this compound was flat as well. So that's a requirement to have an uninterrupted pi cloud. However, because of the relatively large size of the ring, this compound is actually able to take on a non-flat shape, essentially a tub shape, which is shown here, where the sides face up or towards the same direction, which means that the ring itself is not a flat ring. By taking on this non-flat shape, the molecule avoids being anti-aromatic. And as a result, this compound is considered a non-aromatic compound just simply because of its shape. This next compound is 10-annuline, or if you want to use the IUPAC naming system, is cyclodecapentaene. It has 5 double bonds. If this molecule were flat, it would have an uninterrupted pi cloud. And then based on Huckel's rule, we can note that this compound does follow Huckel's rule as well. So if we plug in 2 for the Huckel rule, we can get 10 pi electrons as an acceptable number for an aromatic compound, which this compound does have 10 pi electrons. So this compound would be predicted to be aromatic if it were a flat compound. In reality, though, there are 2 internal hydrogens, which are highlighted here, that are generally facing towards each other to the point that they have a steric interaction across the ring. And so that forces the molecule to take on a non-flat shape, which means this compound in reality is non-aromatic. Interesting example of an aromatic compound is methylene cyclopropene. This is a compound that when you look at it, you'll notice that it is made up solely of carbon and hydrogens. So it's a hydrocarbon. Most hydrocarbons typically have very little dipole moment. So in other words, they're very nonpolar. So their dipole moments usually tends to be around 0 dBs. However, this particular compound, methylene cyclopropene, has a fairly large dipole moment, somewhere around 1.9 dBs. The reason for this has to do with a resonance form, as you'll see in a moment, that is highly polar. The resonance form that is shown first above involves a ring that has a double bond, which of course has 2 pi electrons, and then it also has a carbon that has a double bond, but the double bond is sticking out of the ring. So as far as the number of pi electrons within the ring, there's only 3 pi electrons, so 2 from the double bond, 1 from the double bond that is partially on the ring. So the carbon that is part of that double bond has 1 pi electron. So in total, there are 3 pi electrons in this ring. Based on the ring, it is a fairly small ring. It is flat, and therefore it has an uninterrupted pi cloud. So this compound or this structure follows rule 1 of the aromaticity rules. However, it doesn't follow rule 2. So it has an odd number of electrons. So that means that this compound is neither aromatic or anti-aromatic. It is a non-aromatic compound. Methylene cyclopropene has another resonance structure, which we can draw by moving these electrons from this double bond out towards the carbon, the CH2. That gives it a negative charge on that carbon, and it leaves behind a positive charge on the carbon that was part of the ring of that previous double bond. A carbocation that forms here, you might recall, is an empty p orbital. In other words, there's a p orbital there. The carbon is sp2 hybridized. The p orbital has no electrons, but it allows the pi cloud around this ring to be uninterrupted. So there are p orbitals at the 2 carbons that are part of the double bond. Each one has an electron, so for a total of 2 electrons. On this carbon, where the carbocation is, there's also a p orbital, so that allows an uninterrupted pi cloud around the ring. But because there's no electrons there, we have a total of 2 pi electrons overall in this ring. If we go back to Huckel's rule, which has 4n plus 2 number of pi electrons, that's an acceptable number of electrons for an aromatic compound. If we plug in 0 for that formula, an acceptable number of pi electrons is actually 2. So 4 times 0 plus 2 would be 2. So 2 pi electrons would make this compound aromatic since it also follows rule 1. So Since this resonance structure, although is an odd structure because of the charges, since it is aromatic, it is a large contributing factor to the overall structure of methylene cyclopropene. And this explains why this polarized resonance form leads to a very large dipole moment for methylene cyclopropene. Let's take a look now at how aromaticity rules apply to ionic hydrocarbons. For example, if we take a look at 1,3-cyclopentadiene, we'll notice that this carbon here is not sp2 hybridized, and so this compound itself would be considered a non-aromatic compound since it has an interrupted pi cloud. So there is no p orbital on this carbon to allow the electrons, the pi electrons, to flow around the ring. However, if we add a base, we could remove one of these hydrogens, theoretically, to create this anion shown here. That lone pair would allow this compound to now be aromatic since we already have 4 pi electrons from the double bonds, the 2 double bonds that we have here. And so if we can somehow get another 2 pi electrons, we can make this ring aromatic. And so what happens with this compound is that this carbon will be sp2 hybridized. It will have a p orbital, and that p orbital will have the lone pair on it to allow the completion of the cyclic pi cloud and allow this compound to be aromatic. So as you'll see in a moment with the next few examples we'll look at in this chapter, very often when you have a lone pair, that lone pair can contribute to the compound completing the pi cloud and also be counted in the pi electrons in the pi cloud. Or if it's not beneficial towards the compound, in other words, if it's not going to allow the compound to be aromatic, or maybe if it's going to make the compound anti-aromatic, the lone pair instead would, instead of being in a p orbital, would be usually in an sp2 orbital perpendicular to the pi cloud of the ring, and therefore it won't count towards the electrons that are part of the pi cloud. Another possibility with cyclopentadiene is if the compound loses a hydride, in other words, an H minus, to produce this cation shown here. It has a carbocation on this carbon, and as we discussed before, carbocations are sp2 hybridized. That means that there is a p orbital that is empty on this carbon since it is a carbocation. So there are 0 pi electrons on this carbon, and there's another 4 from the double bond. So overall, there are 4 pi electrons in this compound. And this ring would be predicted to be anti-aromatic. The last example with cyclopentadiene is if the compound lost a hydrogen and left behind a radical, an electron, that is unpaired. That would create this cyclopentadienyl radical. That electron would be counted as part of the pi cloud to give this compound a total of 5 pi electrons. And so this compound is considered a non-aromatic compound since there are an odd number of pi electrons. One last thing that I want to point out with cyclopentadiene, going back to the reaction with base, is that cyclopentadiene is extremely acidic for a hydrocarbon. So most hydrocarbons are fairly non-acidic, so their pKa's are usually about 60, but this one here is very acidic, as we'll discuss in a moment, with a pK of around 15. The next example is cycloheptatriene, which is this compound shown here. These hydrogens on an sp3 carbon, if we were to remove one of them with base, we would leave behind a lone pair with a negative charge. That means that if we count those 2 electrons, we're going to have a total of 8 pi electrons in this ring. So 6 from the double bonds, another 2 from this one. So this anion would be predicted to be anti-aromatic if it's a flat structure. The other possibility would be if we lose a hydride, so an H minus, meaning a hydrogen with a lone pair, leaving behind a carbocation. That creates a cycloheptatrienol cation. It has an empty p orbital, so there's no pi electrons on this carbon. There are 6 from the double bonds for a total of 6 pi electrons. Because of the p orbital on this carbon, you can complete the cyclic pi cloud, and because there's only 6 pi electrons, this compound would be predicted to be aromatic. The last example is if we lose a hydrogen and leave behind a single electron, unpaired electron. In other words, we create a radical as shown here. That lone pair would be counted as in the number of pi electrons, so there would be a total of 7 pi electrons, which would make this compound non-aromatic, so neither aromatic or anti-aromatic, due to the odd number of electrons. Cyclopentadiene is a compound that is a hydrocarbon, and unlike most hydrocarbons, this is a very acidic compound. Most hydrocarbons have a pKa of somewhere around 60. This compound, however, is highly acidic with a pKa of about 15 or 16. If we add sodium hydroxide, which is a base, it will remove one of these protons, resulting in an anion. And because this anion is aromatic, it means it is very, unlike most anions, is very stable and very likely to form. And so the hydrocarbon that we started with is highly acidic because it wants to form this highly stable anion. The compound that we're producing, the anion, is aromatic because we have 4 pi electrons from the double bonds and another 2 from this lone pair that can be placed in a p orbital to complete this pi cloud, and therefore is going to be counted in the number of pi electrons. So you can see this diagram, orbital diagram, with a p orbital at every carbon, and then there's 4 carbons that have a single electron. Those are the carbons that have the double bonds, so there's a p orbital at each one, and there's an electron in each p orbital. And there is 1 carbon, this one, which is shown here, which has another p orbital as well with a lone pair. That allows an uninterrupted pi cloud, and then there are a total of 6 pi electrons within that pi cloud. The hydrogen that is shown here in this carbon with the lone pair is going to be in the same plane as the ring and sort of out of the way of the pi cloud. 1,3,5-cycloheptatriene is a compound that likes to form a cation by losing a hydride. So one of the ways it could do that is by reacting with Br2. So Br2 would result in abstracting a hydrogen and the lone pairs on that hydrogen to produce HBr. And more importantly, leaves behind a carbocation on this carbon. So it produces a cycloheptatrienol cation. This cation, unlike most cations, is very stable because it is an aromatic cation. There are 6 pi electrons from the double bonds that we have in this molecule, and there is an empty p orbital on this carbon, which allows an uninterrupted pi cloud. Since there's no electrons on that carbon, we don't add any more to the count, so there's only 6 pi electrons overall in this pi cloud. Here's a look at the orbital diagram. So every one of the carbons with the double bonds have a p orbital with a single electron, which you can see in this diagram. And there is a 7th carbon, which is where the carbocation is, which has a p orbital, and it is empty. In other words, there's no electrons. That empty p orbital allows the pi cloud to continue around the ring, and there's only a total of 6 pi electrons. So overall, this compound, this cation, is aromatic. In this question, we have an example of applying the aromaticity rules towards a reaction product. So we have cyclooctatetraene, and the question is asking us why it reacts with potassium metal so readily to produce a dianion. So we want to explain why the reaction happens so quickly or easily, and also determine the geometry of this dianion. Cyclooctatetraene is a compound that has 8 carbons in a ring, and it contains also 4 double bonds, as shown here. If we add 2 moles of potassium metal, the metal will add electrons into the ring and form this dianion, which we see here. So the way you could understand this reaction is each carbon of the which has a double bond has an electron, a pi electron within that carbon. And if we add a metal which is capable of donating electrons and becoming a potassium cation, those electrons will be added to one of these carbons, and so we can form a anion at, let's say, 2 of these carbons. Now, what we see here is actually one of several resonance structures we could possibly draw from this dianion. So we could move the lone pair, for example, in this direction, which would force the double bond to move here and create another lone pair. And that can continue around the ring to create other resonance structures. Now, the reason why this reaction happens so readily is because the product is an aromatic compound. So in this product, in this dianion, we have 6 pi electrons from the 3 double bonds we have. And then we have a lone pair which has 2 more electrons here, and another lone pair with another 2 electrons. So if we add all of those electrons, we come up with 10 pi electrons for this ring, which would be an example of an aromatic compound, as long as this compound remains flat, and it will in order to become aromatic. And so the product from this reaction is an aromatic dianion, and so it's really stable. That's the reason why the reaction happens so quickly. As far as the geometry of this molecule, I would suspect that each carbon would be trigonoplanar. It would have a p orbital at every carbon to have an uninterrupted pi cloud. Now the bond angles, just because it's an 8-member ring, would be somewhere around 135 degrees, which is the typical bond angles, the internal bond angles for an octagon. A few examples of aromatic heterocycles. Heterocycles are compounds that contain more than one type of atom, so that's one definition, or another way of looking at it, it contains an atom other than carbon within the ring. Heteroatoms generally will have a lone pair or maybe even 2. Those lone pairs can be counted towards the pi or the pi number of electrons if it's beneficial towards the compound. In other words, if it's going to allow the compound to be aromatic. In some cases, we may not count those lone pairs as in the number of pi electrons, since we want to avoid anti-aromaticity. Here's an example of an aromatic compound. It's called pyridine. It looks very similar to benzene, and we have replaced one of the carbons in benzene with a nitrogen. This compound is an aromatic compound. There are 6 pi electrons just from the double bonds, so we do not need to count the lone pair on the nitrogen. And so in total, this compound will have 6 pi electrons. Since it's a 6-member ring that has an atom that is sp2 hybridized, with a p orbital at every atom in the ring, it's going to be aromatic. Here's how the pi cloud or the orbital diagram looks for this compound. We have a p orbital at every atom in the ring. This is the nitrogen atom here that has a lone pair, shown in green. Each atom within the ring is going to be sp2 hybridized. It's going to have a p orbital. That p orbital will have one single pi electron that allows the double bonds to form. And then on the nitrogen, we have, in addition to that, a lone pair. That lone pair will sit in an sp2 orbital. That sp2 orbital will be in the same plane as the ring itself. And so it's going to be perpendicular to the pi cloud. And so it's out of the way of the pi cloud, and we do not count that lone pair in the number of pi electrons. So there's only 6 pi electrons in total within this ring. Pyrimidine is a compound that, again, looks similar to benzene or even pyridine. We have 4 carbons and 2 nitrogens within the ring. Each carbon will have a double bond, and there's also a double bond here. So in total, there's 3 double bonds, or in other words, 6 pi electrons for this molecule. The lone pairs on the nitrogens are not needed for this compound to be aromatic. And so, as you can see here in green, they're going to be in an sp2 orbital. That sp2 orbital will face away from the pi cloud. So it's going to be in the same plane as the ring, perpendicular to the p orbitals at every atom. And so we do not count those in the pi electrons since they're not part of the pi cloud. There is, however, a p orbital at every atom, including the nitrogens, and that p orbital will have a single electron, which allows the double bonds to form. And so there's a total of 6 pi electrons in this pi cloud, making this compound also aromatic. Let's take a look now at a few examples of 5-member rings and how the aromaticity rules apply to them. First example would be pyrrole, which is this 5-member ring with 4 carbons and a nitrogen. Each carbon contains a double bond, and so there is a p orbital, as you can see by this diagram here. There's a p orbital at every one of these carbons with a single lone pair, which allows those double bonds to form. The nitrogen will be also sp2 hybridized, and it contains a p orbital as well. That p orbital will be in the same plane as the other p orbitals, or will be aligned with the other p orbitals on the carbons. This p orbital on the nitrogen will have a lone pair in that orbital. And so we count those 2 lone pair electrons as part of the pi cloud, giving pyrrole 6 pi electrons. And so this compound is an aromatic compound. Notice that the bond to the hydrogen is formed from an sp2 orbital on the nitrogen overlapping with the 1s orbital on hydrogen. If we compare this orbital diagram to the ones we saw on the previous slide with pyridine and pyrimidine, which contain nitrogens with lone pair as well, you might recall that in those examples, the lone pairs were on an sp2 orbital away from, or as in the same plane as the ring, in other words, away from the pi cloud. And so in pyridine and pyrimidine, we didn't count the lone pair as part of the pi cloud. In the case of pyrrole, we do need to count the lone pair since it's going to allow pyrrole to become an aromatic compound. So it kind of depends on the situation. Sometimes we count the lone pair as part of the pi cloud since we may need it for that compound to be aromatic. In other cases, we may not count the lone pair. Instead, that lone pair will be in an sp2 orbital away from the pi cloud. Imidazole is a molecule that is also aromatic. It has 2 nitrogens and 3 carbons. If we look at the orbital diagram, each carbon, for example, these two, will have a p orbital with a single electron, allowing that double bond to form. The nitrogen here and the carbon here labeled with a 2 will each also have a p orbital with a single electron. Now the lone pair on the nitrogen, which is labeled as position 1, it will be held in a p orbital, so we're going to count those 2 electrons, giving this molecule 6 pi electrons. The lone pair on nitrogen 3, however, is actually in an sp2 orbital, which is perpendicular to the other p orbitals, or to the pi cloud. And so that lone pair, which is shown here in green, will not be counted as part of the pi electrons. As we saw in this chapter, pyridine, which is the 6-member ring with a nitrogen, is an aromatic compound, and the lone pair on the nitrogen is not required for this compound to be aromatic since there are 3 double bonds. In the case of pyrrole, we also have an aromatic compound, but in this case, the lone pair on the nitrogen is actually required or needed to make this compound aromatic since there's only 2 double bonds, and so a lone pair would add another 2 pi electrons, making this compound aromatic. That difference of using the lone pair or not in order to make the compound aromatic or keep it aromatic makes a big difference in how these two amines behave in reactions such as, for example, the reactions that they would undergo with an acid or some electrophile. Pyridine, since the lone pair is not required for aromaticity, tends to be a more basic nitrogen than the one on pyrrole. So when the nitrogen on pyridine reacts with acid, it forms a pyridinium ion, which has a pKa of about 5.2. In the case of pyrrole, this nitrogen lone pair is needed for the compound to be aromatic, and so it has a harder time reacting with acid or even electrophiles in general, since that would mean that we're going to make a bond to either a proton or an electrophile and destroy the lone pair, and we no longer have an aromatic compound when we do that. So the product from a reaction between pyrrole and an acid would be making pyrrolonium, which is shown here. It has a pKa of almost 0, pKa of about 0.4. That means that this compound is more acidic than pyridinium. So that means that this is a weaker base than pyridine. So since this is a weaker acid than pyrrolium, this is a stronger base than pyrrole. That's another way of looking at it. The way we can view this is if we look at the 2 products from the reactions, we have a pyridinium ion that is still aromatic since we didn't need the lone pair for pyridine to be aromatic. So if we tie it up, the lone pair, we tie it up with a proton bond, it doesn't matter since we still have 3 double bonds and the product here is still aromatic. In the case of the product from pyrrole, we have to make a bond between the nitrogen lone pair and a proton, destroying the aromatic ring since that lone pair is no longer available to make this product aromatic. And so that's part of the reason why this compound here is less likely to form, which means pyrrole is less basic. Many of the heteroaromatic compounds that we cover in this section are commonly found in molecules that are part of biological systems. For example, many amino acids and nucleic acid bases contain a pyrimidine and an imidazole ring. So here are a few examples. Here is cytosine, thiamine, uracil, which all contain the 6-member rings with 2 nitrogens, which is essentially derivatives of pyrimidine. And then we have in histidine, which is an amino acid, we have an imidazole ring. Oxygen and sulfur atoms sometimes contribute a lone pair in order to make a molecule aromatic. As an example, thiophene contains a sulfur atom plus another 4 carbon atoms. There are 2 double bonds, so there are 4 pi electrons from those double bonds. And so we need a lone pair from the sulfur atom in order to add a couple of more pi electrons and make this compound aromatic. And so if we look at the orbital picture of this molecule, we have 4 carbon atoms, each with a p orbital containing a single electron, which is what leads to the double bonds in the molecule. And then we have the sulfur atom with 2 lone pairs. One of those lone pairs will sit in a p orbital that will allow this compound to be aromatic. So those 2 electrons will be part of the pi cloud. So thiophene has 6 pi electrons and therefore is an aromatic compound. Note that the other lone pair will be inside of an sp2 orbital and it will be on the plane of the ring. In other words, it will be away from the pi cloud, and so it doesn't add to the total pi electron count. Boron is an atom that in most compounds, it will have 3 bonds coming from it, so it will be trivalent. And in such compounds, boron generally acts like a carbocation in that it contains a p orbital that has 0 electrons in it. And so that p orbital will allow the pi system to continue, involving a compound that is close to being aromatic. However, the p orbital will not have any electrons, and so we don't count any electrons from the boron. An example is borosine, which has 3 nitrogen atoms and 3 boron atoms. The boron atoms are sp2 hybridized, and they will have 0 electrons from the p orbital. These nitrogen atoms, at least in borosine, will be also sp2 hybridized, and the lone pair will be counted in the pi electrons of this compound. And so this particular resonance form has 6 pi electrons and is therefore aromatic. There's another resonance form of borosine that we see here that has partial or has double bonds as well as single bonds. So we can get to that resonance form by using a lone pair, for example, to go in this direction to make a double bond this way. And then this nitrogen will contribute a lone pair into the empty p orbital of the boron to the right of it to make a double bond in that direction. And then this nitrogen atom will contribute a lone pair to make a double bond between the nitrogen and boron. And so we get to this resonance structure that not only has these alternating double and single bonds, but it also has charges. So the nitrogen, because it gave up a lone pair to make the double bond, will have a positive charge. And then the boron, because it is gaining electrons in that double bond, will have now a negative charge, at least a negative formal charge. This resonance structure will also be aromatic, and the way you can count the pi electrons is just simply from the double bonds. So there are 3 double bonds, and so there will be 6 pi electrons. In this question, we're going to look at furan, which is the structure here. It contains 4 carbon atoms and an oxygen atom. Notice that furan is very similar to thiophene. And so we want to show how this compound is aromatic just like thiophene. Furan is a compound that is similar to both thiophene and pyrrole in that it contains 4 carbon atoms and a heteroatom. In the case of furan, we have an oxygen atom that has 2 lone pairs. And because there are 2 double bonds in this molecule, that means that furan has 4 pi electrons just from the double bonds. And so we need to use one of the lone pairs on the oxygen in order to make this compound aromatic with 6 pi electrons. And so the orbital picture of furan looks like this, where we have a p orbital at every atom in the ring. The carbon atoms will have a single electron in each p orbital. The oxygen will have a p orbital with 2 electrons, which is one of the lone pairs on the oxygen atom. The other lone pair will sit in an sp2 orbital, and that sp2 orbital will be in the same plane as the ring or perpendicular to the pi cloud. In this section, we're going to cover some examples of aromatic polycycles. These are compounds that contain multiple rings, and they are also aromatic. An example is naphthalene, which is essentially 2 fused benzene rings together. As you see by the structure, we have 5 double bonds, and therefore we have 10 pi electrons. Notice that the double bonds are also alternating. And so when we look at the orbital diagram of this compound, in particular the p orbitals, there's a p orbital at every carbon atom in the ring. And every one of these p orbitals contains a single electron that allows those double bonds to form. And so overall, this structure is very planar. It's obviously cyclic, and it contains an uninterrupted pi cloud. And because it has 10 pi electrons, naphthalene is an aromatic compound. Note that naphthalene has 3 resonance forms, which you can see here. So starting with this structure, we can move the double bonds clockwise. So this double bond moves this way, this one that way, and so on. So we get to this other resonance form. Notice that the double bond here in the middle is shown on the right side, but we could easily have shown it on the left ring. Another resonance form can be shown by moving the electrons on the right or the ring on the right side of the molecule, as shown here, to give us this other resonance form. All 3 resonance forms are aromatic. Another related example is anthracene. It contains essentially 3 fused benzene rings. If we count the double bonds, we have 7 of them. That means this molecule has 14 pi electrons, and because it has an uninterrupted pi cloud, we have an aromatic compound. Many polycyclic aromatic compounds, such as benzopyrene, are compounds that are considered carcinogenic. The reason for that is, for example, in the case of benzopyrene, it is metabolized in the body by several oxidation reactions that add epoxides as well as alcohols. And so we produce intermediates such as this one here that are able to react with different nucleophiles in the body, such as DNA, that eventually leads to the misinterpretation of DNA during replication and therefore leading to cancerous cells. Other polycyclic aromatic compounds are also carcinogenic because of their flat structure. They're able to also slip in between DNA bases within the DNA molecules, which leads to errors in replicating the molecule, since essentially leads to a kink in the structure while replication occurs. A physician named Percival Pott recognized many centuries ago that certain occupations like chimney sweepers led to an increase of certain types of cancers. It is now known that, at least in the case of chimney sweepers, this is due to the exposure to benzopyrene and other polycyclic aromatic compounds. In this section, we'll cover some examples of aromatic polycyclic heterocycles. These are compounds that contain both a heterocycle and, of course, multiple rings. One example is quinoline, which contains a pyridine attached to a benzene ring. This compound contains 5 double bonds, and so it has 10 pi electrons. The lone pair on the nitrogen is not needed in order to make this compound aromatic, and so that lone pair will be found in an sp2 orbital. Isoquinoline, which is shown here, has also 10 pi electrons. It is due to the fact that the molecule has 5 double bonds. And again, the lone pair on the nitrogen is not needed for this compound to be aromatic, so it sits in an sp2 orbital. Indole is a benzene ring fused together with a pyrrole ring. There are 4 double bonds, giving us 8 pi electrons. So the lone pair on the nitrogen will be used in this case in order to give this compound 10 pi electrons. The lone pair will typically be in a p orbital in order to be part of the pi cloud. Purine, which has 4 nitrogen atoms, has 8 double bonds, so that's 4 double bonds and 8 pi electrons from those double bonds. And so we're going to use the lone pair on nitrogen labeled at position 9 in order to add another 2 pi electrons and make this compound aromatic with a total of 10 pi electrons. Many examples of biological molecules that contain an aromatic polycyclic heterocycle. Here's just a few examples. Tryptophan, which is an amino acid, contains an indole ring. Adenine and guanine, which are, of course, DNA and RNA nucleic acid bases, both contain a purine ring, which you can see here. And then lastly, quinine, which is a potent antimalarial agent, contains a quinoline ring as shown here. Acetylene, which is this beautifully blue-colored hydrocarbon, which is also an isomer of naphthalene, has a 7-member ring fused together with a 5-member ring. Based on this structure, try to determine whether this compound is aromatic or not, and then try to draw another resonance form of this compound. Based on the structure of acetylene, which has 5 double bonds, and the fact that it has alternating double and single bonds, leads us to believe that this compound should be aromatic. So there's a total of 10 pi electrons. Every carbon atom has a p orbital. Since it's part of a double bond, it must be sp2 hybridized, and therefore it must have a p orbital. And so that allows this compound to be aromatic by the fact that it has 10 pi electrons and it has a uninterrupted cyclic pi cloud. A second resonance structure of acetylene is shown here on the right. We can get to that by moving the electrons from the double bonds in this direction. For example, we can move this double bond this way, this one here, this one here, this one here, and this one here.